Hi there, welcome back. Well, I'm going to give you another example of the type of work geological scientists do. I'm going to give you an example as to how to use geologic knowledge uh, to help solve engineering problems. To illustrate this, I have picked a shale that has been problematic in terms of engineering construction in the north central Texas area. It is known as the Del Rio Clay. And just to remind you, my name is Robert Font. I have a PhD uh, in the geological sciences from Texas A&M University. I'm a certified professional geologist with more than 50 years of professional experience and a proud member of the AIPG. The Del Rio Clay is a Cretaceous fossiliferous marine shale that was deposited in fairly shallow waters. One of the key fossils that you find in this shale is the oyster Exogyra aretina. The area where I studied the Del Rio Clay is located in between Austin and Dallas. It's really centered around the Waco area. This region lies along the Balcones Fault Zone, which is a system of normal faults that extends pretty much across the entire state, from Uvalde through San Antonio, Austin, Waco, and into the Dallas area. The table shown here is basically a synopsis of the stratigraphic column of the Cretaceous system in north central Texas, showing you where the Del Rio Clay actually fits. The Del Rio Clay lies below the limestones and the shales of the Austin Chalk and the Eagle Ford, and above the carbonates of the Georgetown limestone. The contact between the Del Rio Clay and the overlying pepper shale of the Woodbine group is a nonconformity. I should tell you that the Del Rio Clay is composed of a gray calcareous plastic clay that may be interbedded with occasional and discontinuous limestone stringers. Uh, these clays flow plastically when wet. They have low shear strength and low slope stability and may form corrosive soils. When exposed along the slopes, it can fail by slumping. A slump is a specific type of landslide that occurs along a well-defined rotational slip surface that approximates a circular arc. When the Del Rio Clay is exposed along slopes, slumps can occur even if these are covered with riprap, like you see on the picture. From a mineralogical point of view, the formation has abundant clay minerals, uh, mainly illite with some smectite and some additional kaolinite. The Del Rio Clay is an over-consolidated, fractured, and fissured shale. Estimates indicate that this formation was at one point covered by more than 2,000 feet of overburden. Currently, it is exposed at the surface or covered by only a few feet of overburden. So it fits the classic definition of overconsolidation. The values of Adalbert limits and indices, swell pressures, clay content, and unit weight for the Del Rio Clay are summarized in the table that is shown here. You can see that the liquid limit values typically range from 60 to 77. Plasticity index ranges from 30 to 52. Swell pressures in pounds per square foot range from 2,000 to about 8,000, and the clay content is typically in the 90% range. Strength tests, typically unconfined compression tests and mainly direct shear tests, were conducted on the Del Rio Clay on both undisturbed and remolded samples. A full spectrum of direct shear tests were conducted on samples of the Del Rio clay. Uh, Now these range from the unconsolidated undrained to the consolidated undrained, uh, consolidated drained, and residual strength tests, simulating various possible field conditions. Values of the cohesive strength and the angles of internal friction, or if you will, the coefficient of friction for initially saturated samples of the Del Rio clay are summarized in the table that you see here. I think it's important to note that typically the angle of internal friction in terms of consolidated undrained tests tends to be larger than the angle of internal friction in terms of the consolidated drain tests. And the sensitivity of these materials is approximately 1. This affirms the fact that this shale is over-consolidated. Residual coefficients of friction for the Del Rio clay range from 0.12 to 0.16. These low values may apply to existing field conditions. Linear Moore envelopes for some of the expected field conditions that we can find in the Del Rio clay are highlighted below. You can see 3 different linear equations here, but I want to point out that the lowest residual strength values for this material are obtained when the shear plane that is developed in the direct shear test coincides with a pre-existing plane of weakness or a plane of anisotropy. In some cases, that is the strength that applies to field conditions. On the picture, the green arrows are pointing to fractures and fissures in the Del Rio clay. As mentioned earlier, landslides in the Del Rio clay typically occur as slumps on the exposed slopes along a well-defined rotational slip surface. The sketch shows you that the slip surface may start at the top of the slope with the development of a tension crack, or it could start on the face of the slope towards the top. Some of the key points to summarize here is that the loading history and geologic history of the Del Rio clay is such that along some slopes, the acting field strength is going to be close to the residual strength. So standard CU and CD tests would yield values of cohesion and coefficients of friction that are higher than those from residual strength tests, or those that may truly be operative in the field under certain conditions. It is obvious that if we use the wrong strength values, that could lead to the misinterpretation of the stability conditions of a slope and to ensuing failures through mass wasting. In the slope stability analysis shown here, using the method of slices, please note that the angle of internal friction that applies to the specific field condition is that which is closely equivalent to the residual strength. Also note that if we were to use values obtained from your typical consolidated drain or consolidated undrained tests, we would have incorrectly predicted the stability of the slope. Well, the main conclusions here then are that proper geological studies and input can and should be integrated in engineering analysis to prevent errors and costly failures. Also, synergistic interaction between geologists and engineers are best to ensure successful ventures. Well, that's it. Hopefully you have learned something. Take care. Bye-bye.